So today we're going to change gears and we're going to talk about something called an infinite geometric series. The difference between finite and infinite is that a finite series has a specific number of terms, whereas an infinite series adds up all of the terms in the entire series. We don't really talk about infinite arithmetic series because with an arithmetic series, your values are always going to be something that we refer to as divergent, or summing to be something like infinity or negative infinity. I mean, think about an arithmetic series for just a second. Maybe the example of something like 2 plus 4 plus 6 plus 8, and you're going to continue on as you add the 10, 12, 14, even the individual terms themselves eventually become something like infinity. So of course when you sum them, they're going to sum to something like infinity or negative infinity, and that's why we say that that's divergent. So we're now going to be dealing again with a geometric series. You're multiplying to go from term to term, and we're going to say that a series is diverging when its sum goes all the way to infinity or negative infinity. We're going to say that it's converging if it's heading towards 0. So if you look at the sum of 2 plus 1 plus a half, eventually those terms are eventually going to come to be so small, we basically refer to them as 0. That's an example of a convergent series. And when we basically chop off all those terms that are basically 0 and add up all the terms that came before them, then we can get an actual finite sum for that infinite series. So what you're going to look at is the absolute value of the common ratio. If the absolute value of the common ratio is greater than 1, then we say that the series is diverging, which means that its sum is going to infinity or negative infinity, and then we actually say that in that case it doesn't have a sum because of the fact that there's no finite value for that sum. And again, absolute value of your ratio. When your absolute value of your ratio is between 0 and 1, then we say that it is convergent, which means that it's going to have a finite sum for those infinite amount of terms. And again, specifically, you're looking for a value that's between 0 and 1 in absolute value, of course. So maybe like a common ratio of 1/2 or 1/4. And again, the reason why that happens is that it eventually makes those terms head towards 0. So the formula that we're going to use to calculate the sum, if it's a converging infinite series, is a1 over 1 minus r. Again, just a little explanation. If you take a look at 2 plus 1 plus a half plus a fourth plus 1/8, again, all those terms head towards 0. So eventually it's almost like we can chop off all those terms when they start to become 0, add up the terms that came before it, and that gives us our finite sum for those infinite terms. So the formula we're going to use is that S equals A1 over 1 minus R, and you'll see that that has some similarities with the formula that we used yesterday, but there is a missing term. So let me explain that for a second. When you have a finite number of geometric terms, your sum comes from doing A1 minus A1R to the n all over 1 minus R. When your common ratio is between 0 and 1, which again gave you a convergent series, that A1R to the n term has a specific value. If each individual one of those values is actually getting smaller every time because of that common ratio being less than 1, that term eventually becomes 0, and that's how we're left with just A1 over 1 minus R. Okay, to show you again the connection between the finite sum formula and what we're going to use today for the infinite sum formula. Keep in mind, once again, you're only using that formula if it's convergent. If it's divergent, then the answer is that there is no sum. So as you take a look at this first example, what you want to do is pull out the common ratio, which is going to come from the base of the exponential term. Okay, so look at that -2. That's your common ratio. You're going to think of it inside of an absolute value. So we're going to take the absolute value of -2. So you're going to take the absolute value of -2, and you're going to see what happens when you compare that to 1. The fact that that is greater than 1 is why we say that this is a divergent geometric series. And the fact that it's divergent means it's not going to have a sum. By the way, if you notice that infinity on the top of the sigma, that's how you know that this is an infinite series and not a finite series. If you have a finite number on the bottom and on the top of your sigma, then you go back to using the formula that we used yesterday. This whole idea of divergent versus convergent is only for situations when the top of the sigma is infinity. So if you look at our second example, Again, the first thing you want to do is identify your common ratio. So the common ratio this time is -1/2 to the n minus 1. Again, the base of the exponent. And you'll see this time this comes out to be less than 1, which is why we say that this is a convergent infinite series. The fact that it's convergent, I can use the formula that we just said on the top left of the screen. The sum comes from doing a1 over 1 minus r. Now be careful, a1 might not actually be what you get when you plug in 1. It's based on whatever you're plugging in on the bottom bound of your sigma. Thankfully, this one is actually 1 that we're plugging in. And so when I do my calculation, you'll see that I end up getting 2 times 1, because anything to the 0 power is 1, or just 2. I'll put that over 1 minus my common ratio, which again is the -1/2. It's important you have that negative in there. Make sure you're careful when you plug it in your calculator. And eventually you'll simplify to get your fraction that gives you the sum of those infinite terms. Okay, so even though you're adding up an infinite number of terms, it comes out to have a finite sum because eventually those terms basically become 0. Okay, so let's take a look at another example. So as you take a look at number 3, again, first thing you want to do is identify what is the common ratio, so 4/3, and then compare the absolute value of that common ratio to 1. You'll see in this case that it comes out to be greater than 1, which is why it is called divergent, and we say that it's no sum. Now be careful, if you use the formula we were using for the convergent one, you'll get a value, but it's not going to represent the sum for that particular series. And then finally our last example, again, pull out the common ratio. It's the base of the exponent. As you compare it to 1, you see that it's less than 1, so that's how we end up with a convergent geometric series. Infinite because of the infinity on the top of your sigma. So you're going to plug into that formula of a1 over 1 minus r. And again, thankfully you're plugging in 1 as the bottom bound on your sigma, so that's how you're able to actually, truly have it be a1. So you put that over 1 minus -3/4. So again, be careful to make sure that you're putting that in parentheses. And eventually you plug in and you'll get the finite value for your sum. So I just want to go back over one last thing. This stuff worked because we were dealing with an infinite geometric series. If I have a finite geometric series, so the top bound of my sigma is not infinity, it's something else, even if it had been divergent as an infinite series, that has no bearing on the sum for that finite series. That finite series, I'm only adding those 5 terms together that you get from plugging in 1 to 5, and you would go back to using our formula from yesterday. Okay, so again, make sure you understand the difference between finite, top bound is a value, and then infinite, top bound is infinite.